It is section 7.2, singular value decomposition, SVD. In this section, we'll study the SVD in detail. Here we have the SVD theorem. A is an m by n real metric with m is larger than or equal to n. Then we can write here A is U sigma V transpose. U satisfy here the U transpose U is identity, and also V satisfy V transpose V is identity. And sigma is a diagonal metric with here sigma 1 to sigma n, and is decreasing order. Here in shape, it is given in this way. A is a tall metric, then U is the same size as A, and sigma and V transpose are square metrics. Okay, here U is called left singular vectors, and sigma is called singular values, and V is the right singular vectors. And sigma are decreasing, and once sigma r plus 1 to sigma n are 0, then we say the rank of A is R. So the rank is the number of non-zero singular values. Here, once the metric is flat, so M is smaller than N, then the SVD can be defined by using A transpose, so that eventually A transpose becomes a tall metric. Okay, and this is a proof for the theorem. And if we have, if you are interested in the mathematical theory, then you may try to read it. We'll jump over here. Now let's consider a little bit around the interpretation of the SVD. Okay, here let the rank of A is R, and now SVD of A is given as U sigma V transpose. Then you have n column vectors, and we have here now sigma is a diagonal of sigma 1 to sigma n, and also V can be written as n column vectors. Now here, and sigma r is the smallest positive eigen value, which means that here rank is R. Okay, so here A is U sigma V transpose. If we multiply V both sides, then AV becomes U sigma. AV, A times V metric multiplication is defined in this way. A and columns of V, and for each column A is multiplied. That is the definition of metric multiplication. Now for U sigma, there's U and sigma. If you multiply this, then you can reach at this one, sigma 1 U1, and second column will be sigma to U2, and so on. And here, by comparing this one, that one, we can reach at here now, A Vj is same as sigma j Uj for j's from 1 to R, and then A Vj equals 0 when j is larger than R. Because over there, from here to there, it must be 0. Okay. The similarly start with A transpose equal V sigma U transpose. We can reach at that algebraic expression. A transpose Uj is sigma j Vj, and j is from 1 to R, and A transpose Uj is 0 when J is larger than R. Okay. From these two equations, now, okay, here, and AVJ and sigma Uj and A transpose Uj and sigma j Vj, from these two equations, we can have some meaningful equation. Now we apply A transpose for that one. Then there is A transpose A Vj equals same as now sigma j A transpose Uj. Now A transpose Uj is sigma j Vj, so that sigma j and sigma j Vj, which is same as sigma j squared and Vj. That means that sigma j squared is an eigenvalue of A transpose A, right? So we reach out this equation for J's from 1 to R. Now similarly, we can have that one. A transpose Uj is sigma j squared Uj. Okay, so here this equation gives how to find the singular values just from the metric A transpose A. Now if we try to find the eigenvalues, then now after finding eigenvalues and take a square root, then that will be singular values. And here, now, okay, so by finding eigenvalues and eigenvectors, in fact, the singular values and the V vectors, so it's a right singular vectors, can be found. And once sigma and V are found by finding eigenvalues and eigenvectors of A transpose A, then U can be obtained by using, okay, here, that, just a moment, where is it? Okay, here, that one, so that U vectors can be obtained from here. Now, Uj equals same as 1 over sigma j and A Vj. After getting sigma and V here, by multiplying this way, you can get Uj, right? Okay. Now, the singular value decomposition, A is now, A is here U sigma V transpose. That can be written in this way. That is called dyadic decomposition. And it's rank 1 matrices are added from 1 to n. Here we have the n columns and V has n columns, so that this one can be written in this way. That is called a dyadic decomposition. Okay, because rank is R, so that rather than n, we can use R here, and this expression has been used for various applications and approximations in the metric analysis. Okay, we have now geometric interpretation of the singular value decomposition. A maps on orthonormal from an orthonormal basis to the scaled orthogonal basis. Okay, let's look at here. Now, look at over there. And here, A and V1 to Vn is the same as now sigma of U1 to sigma u r here, rank r. Okay, so we have that. Okay, so we can say that now A maps on orthonormal basis, V1 to Vn to here, now scaled orthogonal map basis, sigma 1 u1, sigma to u2, and here to sigma r ur. So here the base 1 to base 2, we can write in this way. Now we try to understand this, the transformation. Let's start with a unit sphere as n-1 in Rn, so that here the unit sphere is given in this way, the collection of x such that norm of x is the same as 1. So distance is 1. Now, for every x in the unit sphere, and because now V1 to Vn is a basis, it can be written in this way. For some x1 to xn, it can be written in this way. Now, Ax is now, AV1 is the same as sigma 1 u1, AV2 is the same as sigma to u2, so we can write in this way. Now, we define the yj, sigma j xj, then this can be written in this form. So yj is sigma j xj, so the xj is yj sigma j. So the sphere xj squared is 1 is now, okay, so that xj, so rather than xj, here we are using yj sigma j. So from here, now if you consider sigma j is from 1 to n, now there's yj and sigma j here squared, then it must be 1. However, it's a rank r transformation, so that once it's larger than r, then sigma j is 0. So that we have to truncate. Rather than this one, we have to truncate. So the sigma from j is 1 to r, and yj over sigma j squared. Then, if we try to measure this quantity so that we say it's alpha, then now it's truncated so that it must be less than or equal to 1. Anyway, this is a constant, and this one will make a ellipsoid. So after transformation, the unit sphere will be changed into an ellipsoid. Okay, let's see one example. Here, now we'll try to build the set A Sn-1 by multiplying one factor of A at a time. So after getting singular value decomposition, we multiply V transpose first and sigma and U. Okay, here the A is given in this way. And A is 30 minus 2 minus 1, 2. Its singular value decomposition can be written in this way. Okay, in two-dimensional space, we start with the S1, a circle of radius 1. Now, first we multiply V transpose, then that will make a rotation. So that one is now rotational metric. And now we apply sigma, and then sigma is a scaling in horizontal direction 4 times enlarged. Now that one is almost the same. Its scaling factor is almost 1. So as you can see here now, the circle is enlarged in x direction 4 times larger. And then again, U is now a sort of a rotation metric, so that that one is rotated to become this one. Okay. So here, in general, V transpose is a rotation and sigma is a scaling, and then U is again rotation. So here, for singular value decomposition, each component is acting like here rotation metric and scaling metric, and then here again rotation metric. Okay. Okay, that's the end of the part 1, and we'll continue in the second part. Thank you.